is actually of the order of the energy that is needed to make the electron free from the atom or make it a free electron. So the energy that is needed to excite the electron from phosphorus, say, up to the valence band or co-conduction band. And this energy, which makes a free electron up here, is around 0.04 electron volts. So we put a donor state 0.04 electron volts below the conduction band edge. Remember that Eg for silicon is of the order of 1.12 electron volts, which is a huge energy compared to the 0.04 electron volts here. So you can see that this is very small compared to this energy here of the band gap. So that is why we show the donor state up here, which is only 0.04 electron volts from the edge of the conduction band. So let me give you some group 5 elements, okay? Phosphorus, arsenic, antimony, okay? These are all group 5, which you can add to silicon. And the energy that is needed to free the electron in phosphorus is 0.044, in arsenic is 0.049, and in antimony is even smaller, 0.039. So this is very, very little energy that we need to excite the electron and become a free electron. Okay, and these are examples of donor atoms. These energy, ionization energies, are the energies in silicon when we put these dopants or these group 5 elements in silicon. Now, here again, after donating one of its valence electrons to the crystal, the donor atom now becomes positively charged. So the phosphorus atom or the arsenic atom or the antimony atom gives away its electron, and therefore the remaining protons are more than the number of the electrons in the atom, and therefore the atom now becomes positively charged. And the positive charge, overall positive charge in the atom, is equal to, in magnitude, to the charge of the electron. Also, we know that the number of free electrons per unit volume is equal to the number of added donors or dopant atoms, Nd, per unit volume. Now, if we go back to the equation back there that we did at the beginning of this chapter, which is an equation of this form, N is equal to Nc, that is in any semiconductor. The concentration of free electrons is Nc, and then we have exponential EC, okay, that's the edge of the conduction band, AC, minus EF, okay, where F is the Fermi level, over KT, so divided by KT here. Excuse my writing. So this is EF here, okay, and with the minus sign here, of course, okay. So this is all in a bracket like this. This is the exponent. So if we use this, now if we know in an N-type semiconductor, this N is actually equal to the number of the donors we add, Nd, okay, then we can find the location of the Fermi level, Ec minus Ef. So you immediately see that Ec minus Ef is equal to kBt logarithm Nc over Nd. And if you put Nc, Nd, and you calculate, you will find that Ec minus Ef That is the distance of the Fermi level below the edge of the conduction band is much, much smaller than the middle of the gap. So in an N-type semiconductor, and because ND is large, of the order of 10 to 15 and higher, we find an NC in silicon is of the order of 3 times 10 to 19. If we substitute here, we find EC minus EF of the order of 0.3 electron volts at room temperature. Now, we know that the band gap for silicon is 1.12 electron volts. Therefore, the middle of the gap is around 0.56. And this 0.3 electron volts is less than 0.56, less than the middle of the gap. Therefore, the Fermi level in an N-type semiconductor is up in the top half of the band gap. That is to say, if you go back here, then the Fermi level in this N-type material will be somewhere here, okay, such that this distance is 0.3. This is around 0.3. So it is in the top half of the band gap. That's the Fermi level in an N-type semiconductor. Remember, the Fermi level in an intrinsic semiconductor is almost at the middle of the gap. So that makes sense. If you have the number of electrons and the number of holes in an intrinsic semiconductor equal, then the Fermi level, which tells you about the occupation of its states, is in the middle. Now, if you go to an N-type semiconductor, you have more electrons than you have holes in an N-type. So the Fermi level, since it's a statistical level, it goes nearer to the conduction band in the top half. Okay, so that's the outcome. Now, similarly, you can do the opposite process. Instead of making the semiconductor N-type, instead of increasing the concentration of electrons, instead of having conduction due mostly to electrons, you can reverse the picture and have this happening with positive charge carriers, which are the holes. How do we do that? Instead of adding impurities from group 5, we now add impurities from group 3. So we go around group 4. Remember, the elemental semiconductors are in group 4. Now, to make it N-type, we added atoms from group 5. Now, to make it P-type, P for positive charge. So for holes being the most free carriers. So to make it positive carriers, holes, then we add atoms from group 3, like boron. So boron is group 3. It has 3 electrons in the outermost shell, right? So we know that silicon, for instance, has 4 electrons. So now we need 4 electrons in the bonds, and we only have 3, right, from boron. So what is the net effect? The net effect is we are short of 1 electron here. A short of 1 electron is like having a hole, a positive charge hole available here. So what happens is that this hole becomes a free hole by the boron. Why? Because an electron from here can jump and fill up this hole. Okay? And if the electron fill up this hole, then the hole moves to this point. So it's a free hole, it can move. And then this electron jumps here, and so on, and the hole moves here. So now we have a free hole. Now, the electron that moved from here to here is actually going to reside in the boron atom. So the boron accepts the electron. Remember, the phosphorus atom in an N-type donates an electron. here the boron atom accepts the electron and it becomes negative because we're adding a negative charge here. So it ionizes and becomes negatively charged, and it's therefore called an acceptor. So acceptor, boron is an acceptor, and this other boron is an acceptor, it gives us a free hole. This other boron is an acceptor, it gives us a free hole. So we have more and more free holes equal to the number of free acceptors or free boron atoms that we add. So now we have predominantly positive charge, which are the holes that are conducting. And now if I put 10 to 15 boron atoms in place of silicon atoms, then I have created a concentration of holes P, which is equal to the concentration of acceptor atoms, Na, A for acceptor atoms, and this can be of the order of, say, 10 to 15 per cubic centimeter. Again, what I did here is I increased the number of free carriers from intrinsic to something 5 orders of magnitude. So this is 5 orders of magnitude larger than Ni, which is of the order of 10 to 10 in silicon. So again, I have reduced the resistivity of this material by 5 orders of magnitude. So the resistance goes down from 100 kilo ohms or hundreds of kilo ohms in an intrinsic silicon to a resistance of few ohms in now a p-type silicon where P is more. Okay, so this is called p-type silicon. Boron is called an acceptor. Okay, and what we produce is a free hole generated in the valence band. Okay, this process is viewed as an electron taken out of the valence band, leaving behind a free hole. Okay, boron atom is an atom from group 3, okay, in an elemental semiconductor, and this boron atom is called an acceptor atom, or simply acceptor, because it accepts an electron. The energy of this acceptor state, again, is very small. In other words, the electron needs a very little amount of energy to transit from one bond to this hole, or a hole or an electron needs very little energy to leave the valence band and leave behind a free hole. Okay, so this boron makes the semiconductor, elemental semiconductor, p-type semiconductor. And if we go back to this table here, we see that boron is group 3 and aluminum is group 3, gallium is group 3, indium is group 3. All of these are acceptors, acceptor atoms or acceptors, and they need very little energy, to create a free hole. So again, the energy is very little, very much smaller than the band gap. So here in this table, actually, you have a list of possible donors and possible acceptors in silicon. Okay, and the energy needed to liberate an electron in a donor or form a hole in a p-type. And again, we can attach a state, which we call the acceptor state, very close to the valence band, such that the energy here is of the order of 0.04 just like the energy needed to make a hole. And this 0.04 electron volts is the very small energy needed to for an electron to leave here and go to the acceptor state, the boron maybe, to make it negative, and leave behind a free hole, which is free in the valence band. Again, just like what we thought again, we expect the Fermi level for this p-type semiconductor to be in the lower half, because now we have more holes in the valence band, and therefore we expect the Fermi level for this semiconductor to be in the bottom half, close to the valence band. And indeed, we can see that's the case by simply going to the relationship that we derived before for P. P is the concentration of free holes, and set P equals to Na, which is the concentration of acceptors. And you can immediately see that the Fermi level above the valence band is of this order. So for silicon, we know NV at room temperature, okay? For Na of the order of 10 to 15, we can find EF minus EV of the order of 0.2 electron volts. Again, this is much, much smaller. That's at room temperature. This is much, much smaller than the middle of the gap, which is 0.56 electron volts. So now let's look at this example here. So in summary, what we can do is we can dope a semiconductor, make it N-type or make it P-type. If you want to make it N-type, we should add to an elemental semiconductor, which is group 4 semiconductor, we should add an atom from group 5. And to make it a P-type, to an elemental semiconductor, we should add an atom from group 3, which we call it acceptor. Okay? Here is a semiconductor of energy gap, Eg, equals 1 electron volt. It is doped P-type. So it is doped with acceptors up to 10 to 16 per cubic centimeter. Okay? The room temperature, which is 300 Kelvin, effective density of states for the conduction band, which is Nc, is this much, 10 to 19 per cubic centimeter. And the room temperature effective density of states for the valence band is Nv equals 5 times 10 to 18. If this material were not doped, what would be the intrinsic populations at room temperature? So let's first assume that it is not doped. Just a semiconductor of band gap equals to 1 electron volts, and at room temperature, which is 300 Kelvin, what is the intrinsic carrier concentration? What's the concentration of electrons and holes? So we go back to the relations we studied in this chapter, and we find Ni, the intrinsic carrier concentration. It's equal to the square root of the product Nc times Nv times exponential minus Eg over 2 kBt. So now we have Eg, we have Nv, we have Nc, we have Kb, and we have temperature. So we just substitute here Nc 10 to 19 per cubic centimeter, here Nv 5 times 10 to minus 10 to 18 per cubic centimeter. Here is 1 electron volts for Eg. Here is 8.62 times 10 to minus 5 electron volts per Kelvin for K, Boltzmann constant, and here is 300 K for temperature. And so when we substitute, we find Na or Ni, the intrinsic carrier concentration, equals to 2.8 times 10 to 10 per cubic centimeter. Now, this gives us a resistance of the order of hundreds of kilo ohms for this material. Now, the next question is calculate the band populations N and P at room temperature for this p-type dope semiconductor. Now we want to dope it with Na. So what is the carrier concentration? So we go to this part. Now if we dope it with acceptors, the concentration of acceptors is Na, which is 10 to 16, then the concentration of free holes, because each acceptor gives a free hole, then the concentration of free holes in this p-type material is going to be 10 to 16, which is the same concentration as the acceptors. Also, we know that N times P is always equal to Ni squared. We have already determined Ni, so we will substitute Ni here, and we have now determined P, so we will substitute 10 to 16 here, and we can determine NP as Ni squared over P. So it is 2.8 times 10 to 10 squared divided by 10 to 16, and we get 7.8 times 10 to 4 for the concentration of electrons. So in this material, we have 10 to 16 holes per cubic centimeter, but we only have 7.84 times 10 to 4 electrons per cubic centimeter. So the holes are almost 11 orders of magnitude, or more than 11 orders of magnitude higher than electrons. That is why this material is called p-type, and all the conduction is dominated by holes. So this is how we dope materials, and this is how we make a semiconductor more conductive. So what we will do, we will now stop here or conclude this chapter here, and we will be now ready to move on to chapter 5 next.